can give you the background. Professor, mining engineering, he's been working in the world of rock mechanics, DFN expert for a very, very long time. But one of the things that he has been doing recently, which is fantastic, and I did see a bit of this discussion back in Rock Engine in the summertime, has been spending a reasonable amount of time thinking about the philosophy of the stuff that we do. Why are we doing it? Why do we make decisions in certain ways? What are some of those decisions that we make, and where's the root of some of those decisions? And one of them relates to this journey of GSI, and so it was great that he sort of volunteered to give us a chat. And so with that, if you want to add more about, and this background, but I'll leave that to you. But so join me in welcoming Dr. Elmo. Thanks very much.
Okay. Good afternoon, everyone. So as Professor, I cannot really pronounce this. Rick is okay.
Rick
Thanks.
Good, yeah.
Rick. My name is Davide Elmo. I'm a professor at UBC, and I joined UBC in 2012, so already 11 years. So,
the camera is off.
So you don't see me.
Yes.
Okay, I'm not sure if it's good or bad that they see me. So, yeah, they can actually see me now. I'm not sure if it's good or bad. They can see me. Okay.
You're live.
Then, so as I said, I've been at UBC 11 years now. Time flies. And before that, I was working with Gould Associate. I was a rock mechanics specialist, and then I did my postdoc SFU. And all my background kind of education is mixed between Italy and UK. My PhD is from UK. Actually, I finished my bachelor in the UK as well. So as Rick said, in the last 2-3 years, I started working on this kind of philosophy applied to rock engineering. And everything started actually because my 2 kids were born, and I started basically interested to know like how actually kids learn. At the same time, my students were working on machine learning. So like, how can a machine learn? How can a kid learn? So it's more philosophy, but that's what basically my kind of interest in this topic started. And actually, I mean, kind of more introduction about me. As I said, like, I'm originally from Italy. I think I came up to be an engineer almost by chance. It's like I didn't really never even dream to become a rock mechanics engineer. I want to fly planes. I got glasses. I can't fly planes for a reason. I ride motorbikes, though. Those, yes. I'm from Bologna. That's where the Ducati comes from. So that at least I managed to get that dream fulfilled. But one thing also that maybe kind of differentiate me from other engineers, that my hobby is history and philosophy, which is kind of maybe strange for an engineer. But I really like to read books about philosophy and behavioral, basically science, and that's where basically my kind of interest on this topic begins. So that's maybe explain my non-conventional approach to rock engineering problems. And that's why basically kind of points to this, for me, to this importance of engineering knowledge. So what is knowledge, and more importantly, what is knowledge in the context of engineering? How we know what we know and how we use what we know. So, and also the travel basically to me begins because we're using more and more digital tools in rock engineering, and probably in geotechnical engineering in general. So we have new technology, and we introduce new technology upon basically a framework which is very empirical. And it's very old. I mean, we talk about 40, 50 years, almost even predates basically when I was born. So, and if it's empirical, automatically it's going to have human bias. Everything that is inductive based on experience, by definition, is going to have human bias. And even if you look at the example from the computer science, think about Amazon, Google, the struggle they have actually with artificial intelligence to make it unbiased. Amazon, I think, had to scrap an entire system where they were actually looking at kind of artificial intelligence, looking at going through resume, and that system was very, very biased. Other systems for basically face recognition, we know they're very biased. So they struggle. Imagine us basically with a rock engineering, which is already empirical on its own, how you get this new technology to work with that. So we have these old systems, and is it basically still meaningful to use these systems? So have you ever stopped and asked, how did you develop this system? What is the data used to develop those systems? And that data actually, I think maybe someone has it somewhere, but it's not available. There's no way for you to go back and say, let me try again the system, see if I can basically replicate what they've done. And then finally, because I work at universities, like, how do I put this in context of education? I need to teach my students rock engineering. Should I keep teaching the old stuff? I want to teach new things, and how do I combine those things together? This is, to me, is very kind of important. And how do I teach my students that you have engineering knowledge, the empirical knowledge, and the scientific knowledge? They're kind of really different. And that's why I make a joke with this cartoon. Eventually, someone has to acknowledge the elephant in the room. There are things that we do and they're not really correct, but we're kind of sometimes afraid to say that. And when it comes to knowledge, I mean, the first slides actually you're gonna see that they don't really relate much to rock engineering. And I remember presenting this one to Rock Eng, going on stage, and I realized people were looking at me like, what is the rock? You don't have any picture whatsoever about rock. So maybe I should just put a picture of rock just for the sake of kind of change a bit the scenario, but we're going to focus most on knowledge and philosophy, and then really we're going to switch to rock engineering. And one thing I learned is that with knowledge is that you have the scientific knowledge, you would assume it works everywhere in the world. Force equal mass time acceleration, we all knowledge stays the same, no matter where you are in the world. Everyone's going to teach that. But when it comes to engineering knowledge, particularly empirical engineering knowledge, every person's got different ways to teach it, different opinions. The learning from someone, which learning from someone becomes almost like kind of oral knowledge. So everything potentially is different from whatever country you come from. Maybe they prefer some system, they prefer other system. Europe, you have Eurocode 7. We don't have Eurocode 7 here. So if you look, for example, books I remember from East Europe, they didn't have anything about RMR and GSI, at least that I'm not aware of. If you go, I think even China now, they do more, but at the beginning it was not there. So everything we do is more like local. And I give another example, like if you work with companies, they do core logging. Company A has this manual, company B is this manual. You would imagine its core logging should be the same, but you're going to see differences. So scientific knowledge is not basically, scientific knowledge is supposed to be the same everywhere. Engineering knowledge depends on local, basically, procedure, policy, different, even regulation due to basically the profession of engineers. And one thing that I really like about the philosophy is actually how you can actually look at the problem from a really kind of standing back from it. And one thing that I really like was reading actually Plato, and it's got this short story in the Republic. And if you're not familiar with the allegory of the cave of Plato, it's basically the story that about where people see the world basically through basically shadows cast basically from a fire that stands behind them. You have people holding some objects. They are here, for example, in front of me, there's people, I stand behind, there's a fire, they see only the shadow projecting the wall. So for them, the world is just basically the projection of those shadows. In the story, one of those people in the cave eventually come out of the cave, they start to see the real objects. You see actually what reality is for, it goes back in the cave, he tries to explain to people, this is not real, that's real, and people don't believe him. Because that's what I see, I don't believe based on what is actually out there. In a way, that's what we have in rock engineering. It's always about, this is what we use, I don't really want to see new things. And most of the stuff that we actually do in rock engineering is qualitative. You have quality and quantity are very different. If it's qualitative, depends on the person assessing, basically the parameter or the type of basically method that you use. So I kind of play a bit of I'm kind of having a little bit of fun with that allegory of the cave, and I kind of imagine all the engineers sitting inside the cave. What they see is basically the shadows of what they see in the core boxes. Imagine your idea of the rock mass is a core box, which is a very actually limited information. And most of the stuff you get from core box is qualitative. RMR is qualitative, GSI is qualitative, even RQD technically is qualitative. It looks like a number, but when we dig deep, if you're going to see in the RQD, it's just a quality. So we see all these quantification or qualitative assessments, And now we start also playing with machine learning, statistical analysis. And we do forget that everything we do is not just a real number, not a measurement. And the chains that actually hold us in the cave is basically this kind of bias, the fact that we don't really want to change the systems. Moving kind of close to present, that was Plato. This is actually Francis Bacon, so still like 600 years ago, but Francis Bacon wrote about what we call the idols of the mind. So more on the psychology side, but it's very important because you see that he envisioned 4 different types of idols. Overall, it falls under the category of idols of the mind. And what we're going to see, this is actually what we see as obstacle to innovation, obstacle to learning. The first of these idols is the idols of the tribe. Think about it. Everything we see is basically, we see through our eyes, through our observation. Unless you're measuring, let's say, the length of this table with a ruler, this is a measurement. But if anything is based on rock mass quality or a jointing condition, where if it's this strength, I give you this rating, this one give you this rating, that's quality. It's not real measurements. So you filter the information through your mind. We are humans, so automatically we are biased. So we basically see things through our mind, and therefore it's subjective. And it's very difficult to remove subjectivity from qualitative data. Then you have the idols of the cave, which is where it relates to Plato, but now you create arguments to fit basically your experience. And this is where we're going to give an example for the RQD later. We use something, therefore is correct. This is the tendency we do in rock engineering all the time. When you try to criticize system, people are going to say, yeah, but we use it, we've been using it for 20 years, why should we change it? It works. That's not really scientific validation. And then you have the idols of the marketplace. I mean, I would say probably artificial intelligence, machine learning, that's what it fits. It's very cool to say machine learning. You give it the impression that the machine is learning something and the machine is going to be perfect. Whatever comes out of the machine is correct. And you can actually try now, I'm pretty sure you know about ChatGPT. Try to put some prompt in ChatGPT about rock engineering problems, and you're going to see how many things actually are not correct. So, and I've tried actually with GSI and asked who developed the GSI. He gave me the names of 2 professors in Sweden that don't exist. So it's like, okay, I'm not sure where you get your information, but see, but still it's cool, it's artificial intelligence. And if you want to sell a product, it's really good. I mean, try to write a proposal now that doesn't contain the words artificial intelligence, machine learning. It's easier to get basically funds if you push that kind of basically buzzwords. And then you have the others of the theater, basically this kind of acceptance. I do it, I'm basically the senior engineer or the senior professor, we do it because I like it. And I will not basically back down. So we shouldn't do it, but this is basically what happens. So still in relation to philosophy, but now we're looking at models. Now, and actually one of the questions that was today during the defense was verification, validation, what's the difference? So now here we're going to look at calibration and validation. If you do numerical analysis, everyone's going to ask you, did you calibrate your model? But then they assume that actually the calibration is equal to validation. And what is actually validated? And look at this simple, not really simple, but conception we had of the universe. This is the Ptolemaic basically system to look at basically how planets basically, and the sun rotates around Earth. For 1400 years, people were convinced that Earth is at the middle, in the center, everything rotates around Earth. The point is, this system we know is wrong, but it can actually be useful to predict planetary motions. It's technically calibrated. So very complicated, very convoluted. The mechanism is completely wrong, the assumption, but it gives you reasonable results. Then you have the heliocentric model. We place sun in the middle now. Everything else revolves around the sun. Still, the predictions are not really different from the model from Ptolemy, But if you look at the system also, it's not correct. Orbits are not circular. So still, if you really have to pick one of the two, how do you know which one to pick? Because it gives you almost the same solution at the level of the universe, our basically solar system, of course. So both of them could be set calibrated. Technically, none of them actually validated because the mechanism they imply is actually wrong. And we go back to this kind of idols of the marketplace. When Galileo tried to say, I'm going to use the heliocentric model versus the geocentric model, the reaction that he got from the Spanish Inquisition was that, no, you cannot do it. We don't really look at whether it's right or wrong. We tell you it's not right. You cannot use it. So Spanish Inquisition didn't take it very well. So it's more like a dogmatic kind of approach to science. So what kind of lesson can we learn here that we can actually use now at rock engineering? Yes, your model can be calibrated, where it basically says, I put these parameters, I get this deformation, these are the deformation I get in the field. How do you know that those parameters are actually correct? How do you know you actually capture the right mechanism in the model? And think about, like, if you use FLAC, 3D, any other software, try to look at the same problem with different software. And you're going to see that people's going to use different properties to come up to the same solution. So what does it tell you about the properties that we use? And I'm starting actually thinking that the concept of rock mass strength is not real. It's dependent on whatever system you are basically referred to. And I think that I put another, I think I removed it here, but it was actually another very kind of point directed to the DFM models. We don't really validate DFM models at all. If you look at many things in the literature, we throw fractures in a box, we put in the geomechanical model, but then we don't validate the DFM model. And we assume because the geomechanical model gives me the correct results in terms of deformation, the DFM must be validated. But it's actually more complex than that to validate the DFM model. And this brings us to this kind of, let's call it kind of social experiment in a way. So, I mean, if you've already seen the presentation in RockEng, I mean, unfortunately, kind of spoiler alert there, but look at these two charts, okay? And this is a new system I want to propose. So kind of a challenge. I came up with this new system to do rock mass quality. Very simple. 0 is very bad quality, 100 is very good quality. I'm trying to publish in a paper. And of course, one of the reviewers is going to ask, well, you need to validate, you need to justify what you're trying to do. So I'm going to basically show that I can basically relate my rock mass quality index to some kind of a measured parameters, some seismic velocity. But when I do it, and I use this three-dimensional sonic velocity divided by lab sonic velocity, the scatter is not really good. Yes, I can see a trend. I mean, the R square is not really high, but lots of data here, very few data here on the low quality. Yes, there is a trend, but you can't really say this is actually a very good kind of difficult to say one unique correlation. So I want to make it a little bit better. Let's me kind of do some cosmetic analysis. I throw away almost 50% of my data. I'm not going to tell you why. I'm not going to tell you which data I'm going to throw away. And I'm going to come up with this one. R squared doesn't change, but I got rid of this kind of relationship to kind of, let's call it outliers here, less concentration here. Still kind of variable, but looks a little bit better, visually looks better. So, and notice that is linear, here I just simply change it to exponential. Again, I'm not providing any explanation about that. So, is this acceptable? If you were a reviewer, what would you say to me? Accept, major correction, reject? Like, you think you have to do more explanation about this? So this is not made up. This is the RQD. When they justify the 10 centimeter threshold in RQD, they use these parameters. Initially it was 15 centimeters. They said, not really good. I mean, scatter, let me get rid of some data, and 10 centimeters looks better now. These charts are hidden in a report from 1988. You literally have to dig them up almost at the end of the report, 100 pages report. How many of you actually seen this one? in university. Everyone's going to sell you the RQD with 10 centimeter threshold, but no one explains you why. And if you look carefully, it's just based on personal preference. 15, 10 centimeters, which should be actually be 4 inches because everything was an inch at that time. So you can see that is no scientific validation here. But when you ask engineers, they're going to say, we use it, therefore it's correct. So we know we have many limitations and still we want to use it. So that's also the thing that we get so attached to it. That's what we call preferential attachment bias, that we don't want to give it up. There was a paper in 2017, and the second author actually was Bignaschi of that paper, where they were questioning, should we use RQD or should we use fractal frequency? And that paper became, basically now is forgotten. There's big push, I remember, from the industry saying, no, we need to keep using RQD because it ends up in RMR and ends up in Q, and try to criticize the Q. So that's the problem. So we got attached to it, but you can't say it's validated. So there's no really scientific validation for RQD. I always like, I don't think I have it here, but in another presentation, I make kind of a joke with the Schrodinger cat, like, unless you find a way to really go back in time, recreate the condition under which they developed the RQD, you can't say it's right or wrong. So we can believe it's right or believe it's wrong. So, and both of us will actually be correct. Another problem that we have, and this is actually basically a knowledge, is actually work from Professor Harrison from U of T. And I saw this table first in 2017 when he presented at the conference. And really kind of made me think about some of the limitation of the work I was doing. You have different scale of measurements. You have qualitative assessments, quantitative measurements. And that's okay. I mean, we can live with that. The problem is that the statistics that you can do with it is different. You cannot really do mean standard deviation for qualitative assessment. You can do number of cases, mode, percentile, median, but you cannot really do statistics with this. So if you cannot do statistics, you cannot do design based on statistics. The problem is that RMR, Q, GSI, even RQD, they all fall in this category. You have a quality, you attach a number to it. It's a classification tool, and there's no problem with classification as long as you use them in classification. But if you use as numbers, then technically you cannot do statistical analysis. So many books actually shows that you can do statistical design with GSI, but technically you shouldn't do a standard deviation of GSI. And we did an experiment where we gave the same outcrop to, now it's more than 16. We initially was 16 people, and now we do it with all the graduate undergrad students in my class. And every time we give this outcrop, first of all, they don't realize that we give them an outcrop like this. And then we take subsection of the outcrop, and kind of a tricky, we try to trick them. We flip the image, looks at mirror image, so they don't recognize it's the same outcrop, and we slightly decolor the outcrop, and we ask them to get the GSI for the outcrop. We say it's good condition, just looking at structural character, and we get a plus or minus 30 in GSI. And they even say this is different from this one, is different from this one. They don't even recognize that. So imagine now if you do even image recognition with machine learning to solve this problem. So there's variability, we can live with the variability, but you cannot really do statistical analysis. And one problem that we have also is that we like correlation. I mean, look at any kind of empirical design, people like to plot an X and Y plot, draw a line, something, Y is equal something, Fx. These are all the correlation between Q and RMR. So you can see in the literature, when you plot them on a chart, they're a little bit all over the place. And if I look at the comparison just on a qualitative basis, like what is very poor in RMR and extremely poor in Q, they're not even aligned with that. And the reason why, if you actually look at the database for RMR and Q, most of the database is here. There's very few cases of very low RMR and very low Q, or very high RMR and very high Q. Most of the rock masses close to surface are jointed, so they all line up here. So that's actually where you get probably better correlation. But falls apart here, easily falls apart there because the database does not include the data. So be careful if you just look at correlation because, and also how can you correlate something that's so different as RMR and Q? Because they're very different. So you can correlate the quality. It's like it's good and it's good. That's why you should correlate. But you don't want to have just an equation which looks at those. And the other thing actually, well, I think it's later going to give another example with RMR and GSI. Another thing I've seen, and this actually unfortunately comes from a real consulting project, where they had two sets of borehole data. In one set they had RMR, the other set only had RQD. They were desperate to get the RMR, so they said, let's correlate the two, and we get the correlation to get now RMR from RQD. So it's like, you shouldn't really do that. I mean, of course there's a correlation because RMR is RQD ratings. If your RQD is 100, your rating becomes 20 in RMR 89. So of course there's a little bit increase, but look at the scatter. So not only that, mathematically it's not correct because RMR has RQD in it. So if you do it as a mathematical expression, you have a Y already includes the X in the definition. So it cannot be another F the X later on. So that was the other problem. And this one basically brings us actually to the problem really at ends, which is the GSI. If you really want to quantify something, it means that you measure it. A quantity, it means basically something you can measure, not something you assess in a qualitative way. So if GSI was a true quantity, then it shouldn't depend on experience. As soon as you say depends on experience, then it's a quality. So you cannot measure it. So again, some jokes with the about basically the fact that we're using qualitative data all the time and we pretend they're quantitative data, but we don't tell the senior engineer that actually are qualitative data. So either then the rock mass property is a physical property, so you just need to measure it. That's fine. You need to find a tool to measure it. But if you say it depends on experience, there is a quality. And automatically then you cannot measure it, so you cannot quantify it. And I know it sounds lots of semantic just about the words, but I always basically kind of joke, not much joke, actually very seriously. What happens if there's a problem, like could be a rock fall or an accident in a mine, and you get involved with an expert witness? Someone maybe got killed in the accident. You have to be very careful because lawyers look at the words and they're going to really destroy you in the words. They're going to say, did you quantify? But you cannot quantify. So that's really where the danger lies. Like between ourselves, we can say just semantic, but there's actually a level where you have to be very careful with the words. And that's why to me it's like, if everything's a quality, then how do you define probability of failure then? Because the probability of failure is based on measurements. So how do you know basically something is exactly based on factor safety of X if everything is based on using qualitative assessment? So on terms of GSI, you probably look at, if you look at the literature, there's a list. I think we found 29 different methods to quantify GSI in the literature. It makes it for an interesting reading because you try to compare the different formula, they actually don't balance it out, the formula. People then put like decimal figures to GSI, which is kind of definitely not recommended. And what's actually interesting to see that sometimes you see these quantification methods, but the tools they use to quantify is actually a quality. There's one example where they use persistence. How do you measure the persistence of a joint? If you don't have persistence, then you cannot quantify GSI. Jointing condition, it's very qualitative. So you cannot quantify something if one of the variables that you use is still a quality. And the other thing that it seems actually more interesting is that when they try to justify, look, our quantitative method really kind of agrees with the observational method where people just do it based on the standard GSI table, everything is plus or minus 10. So what's the advantage? If everything is still plus or minus 10, there's no advantage of quantifying anything because it means that just looking at the original GSI table gives you a good estimate anyway. So it doesn't really stand up the idea that you need more experience to get GSI because, again, I don't really see kind of good justification here to say the quantification inverted comma method actually is better than the standard GSI table. And actually on that one, if you think about it, sorry, it's not on the slides, I'm going to put it here. If you look at the original definition 1994 for GSI, was GSI equal RMR 76, so the 1976 version of RMR, or GSI for RMR greater than 23, 89 version minus 5. And before, RMR 76 is equal to this one. Big question mark. Because you cannot really say this. They're very different tables. So if this is true and this is true, then this must be true. Unless it's unidirectional. So only this one and you can't use it at the same time. So that's why we have to be very careful not to play with math. We have all these formulas, then we try to combine them, don't really adds up anymore. And the other thing that to me was interesting, I mean, I've been using GSI for many years, and only in the last 2 years, start kind of focusing on this. So it's like, when I look at the table, it kind of, to me, seems now odd that you give the same quality to very different rock masses. Very massive rock mass with poor gold, basically with a fair good jointing condition, and a very blocky rock mass with good jointing condition, technically gives you the same figure envelope. So very different quality, very different structural characteristics, but the same figure envelope. That to me is a little bit not really clear how you can actually come up with that. So how is it possible very different condition gives you the same quality? And remember, these numbers, actually, those are still RMR. The number in the GSI table are nothing but RMR values, actually, if you look at the way it was introduced. And what they done, they basically just draw these lines. So I started looking at this table, I said, like, how can we get the same quality for very different condition? Because if this quality ends up in a flat model, then you don't know which one is which. If I tell you the GSI of a rock mass is 65 and nothing else, you cannot tell me what is the geology. You only have a number, but you don't have the geological information. So I was looking at this simple kind of analysis. I said, if I take this one's properties and I say XY and XY1 and or XI and Y1 based on properties, and I put in a matrix format, and I multiply the property X times Y or Y times X, doesn't matter, I get that kind of matrix. And I was saying, okay, quality 10, quality 6, quality 10, 9, 8, 7, 6. So these are still quality numbers. If I multiply them, I get this kind of matrix, which is very similar to the GSI. So you can see the diagonals, basically this cell is equal to that cell, this one is basically this one is equal to this one. There's some small variation, but if you look at the original GSI table, actually those small variations. If I divide, instead of doing multiplication, I do y divided by x, I get this matrix where the diagonal is always 1. And then the numbers, now they're basically different. The I and low, or it could be, if I do x divided by y, it would be low and I. But this is very different from this one. So this is this kind of approach. It's not this approach. But what is interesting that this recently there has been some work by it was Marinos and Carter and Marinos, it's two different papers, where they combine the geology of different sites with the GSI table, and they come up with this trend. If you look carefully, they're literally opposite to the actual lines of the GSI. So if I take now the geological trends, they don't really match the initial kind of definition of the GSI table, but they resemble actually this one. So this kind of diagonal that splits two type of behavior, and a trend which I call it go from top left to bottom right, so basically opposite diagonal. So what we done was take this one, try to get new basically trends, but still using the old GSI, so we didn't really change the GSI. Transform that into basically new geological trends. Clearly, this don't really exist, never been observed in the field, so we can just blank them out. We have a different kind of transition because it looks like different rock types behave differently. So the geology is back into the GSI. And we propose this very qualitative version. We said this is 90 plus or minus 5, 80 plus or minus 5. So now this is actually different from this one. Although it's still plus or minus because it's quality, but it's a little bit different the way we interpret it. And what it was kind of interesting that some people start questioning, like, well, you need to validate this table. But this is nothing, especially the GSI, we didn't really change GSI. It's just a different interpretation, not much different from the actual quantification methods. So my conclusion would be, you don't really need to change even GSI. You don't even need to use this one. As long as you're careful with the geology, you know basically that you can still use the original GSI table. And you're not going to need more kind of precision or accuracy than that. Actually, at that point, you can have an accurate GSI because many people get you more something similar, but you cannot have a precise GSI because we don't know what is the real GSI of a rock mass anyway. So in conclusion, I think we need to basically recognize that everything we do is subjective, is based on quality. So you're always going to have human factors at play. They will not disappear, even if you use machine learning. We need to make sure that we recognize that our education, our approach to design influence the way basically we actually even teach rock engineering. And engineering methods are not universal. So there's no really universal method in rock engineering. When it comes to specifically to GSI, to me, it's like, why we cannot live with the original GSI table? Why we have to always find something else to kind of quantify something that it cannot really be quantified? So why we don't like variability? I mean, why we cannot say GSI equal 60 plus or minus 5 and take variability in your design? Because there's always variability. If you do different models, you know that every time you click run, you get a different realization that looks different, but with the same statistics. But they can actually behave very differently if you put in a geomechanical model. So, and the way I summarize things is this one. It's like rock engineering design is literally like flying a plane or building a plane as you fly it. You don't build a prototype and then you see if it works or not. The point is you excavate the rock, you're making a hole in the ground. You're not building a prototype of a tunnel. You don't build a prototype of a slope. And you cannot do it because it's scale dependent. So we don't have prototypes. And that's really what is really kind of limiting, but at the same time makes our field more challenging because challenging more interesting. So these are references that I use in the to build basically the presentation, although they were not maybe specifically listed in the paper in the presentation. So any questions? I guess you can check if there's any questions online. Yeah.
Philosopher and no, there we go. Philosopher.
Thank you very much. I love this presentation. So let's if we go with quantitative model, or if we do, how do you verify this?
That's another problem, because think about it, like if you build a slope, like you start excavating the slope, the validation means that it's based on future data. You can do a back analysis if you have something that failed, or you can say, I'm collecting monitoring data, so I can see today my model is being updated, it matches. But how do you do like long-term prediction? To do long-term prediction validation, you need future data that we don't have. So, and I think that it's not limited to rock engineering. Any models, you cannot really make long-term forecast, because eventually things may change. Even with weather forecast, they keep updating the model. So they say 14 days, and then I feed you data, and then that basically get better and better. And they have an advantage. It's based on real measurements, weather, not like us, which is based on quality. So I always say, like, you cannot really say, my model matches what happened 10 years ago with the failure, therefore now my model is going to work in the future. Because, yes, you validated for a past failure, it's already happened, you're not going to be able to do anything about it. So how is it going to help me now? How do I know that my property is going to work in the future? So I always call it like this idea that you always have to basically feed more and more data to your model every day. And then that's where the calibration comes. You keep calibrating, and eventually you should be able to at least narrow down maybe the range of outcomes. But in rock engineering, what really kind of caused the failure is not what you know, it's what you don't know. If there's something that you didn't measure, like a fault or something, and you don't know about it, that's what really is going to basically ruin your sleep. So it's what you don't know that is the problem. It's not what you know. So if you know, you can constrain it. Like it's kind of unknown unknowns. I was trying to actually explain to my students what is an unknown unknown. Something that you don't know that you don't know. There's plenty of cases with failure, where there were failure planes, geology, that we didn't even know about it, and that's really what happened. Those caused the failure. But if you don't know, if you have geological indicators, you can say, let me try to do some drilling. But if even you don't have those geological indicators, you're going to say, well, it looks okay, until it fails. And hopefully, or maybe it doesn't fail, but most of the system we use, they're so conservative. I think they were kind of protected in a way.
But then in the world of today's world of sort of rapid data and surveillance, LiDAR data sets scanned every whatever and stuff. You see the increasing role for that kind of stuff in this thing. You're looking for quantification. Yes, machine learning it's just a numerical tool allows you to assemble all that data. You see an increasing role then when you approach rock engineering in these real-time surveillance kind of thing, just throws data at you like crazy.
I think the question is like is how you collect the data, which data you're going to collect, because you can have lots of data with photogrammetry or laser scanning. Actually, probably point clouds are better. But then you have to fit into a model. Today, the discussion in Hubble is like, if the model takes 3 days to run, I'm already basically 3 days old by the time I collect my data. And the problem I have, is that we use a lot of tools in a reactive mode. Like, when you look at open pit mining, you have the ground stability radar. They're great tools because are there for safety reasons. So people get out in time, no one gets injured, but they're not there to stop the failure. The failure is going to happen. So, and that's the problem. Like, I was doing another paper and I made a kind of an analogy. Imagine someone tells you, I'm going on a plane, I shouldn't say that, but like you go on a plane and the pilot says, we have a problem. I think there's a problem with the plane, but we are monitoring everything. And we're not going to land. We just keep going. We keep monitoring. We keep adding data to our simulation. And 2 hours later said, the problem is actually going to get worse and worse. Get your parachute, get out. So everyone is safe, but the plane is going to crash. So that's I think the approach we use. Like, we don't really find a ways to avoid the failure in the first place. And in open pit, I guess, is because when you're constrained by economics, you have to make it as steep as possible. So it's not a natural slope that adjusts itself. Well, there's economics behind. So, and that's, so you work in a reactive mode, like it's a, I'm going to make it as steep as possible. No one's getting injured, which is good. And hopefully no one's going to fail. I shouldn't say hopefully, but it's
Just really intrigued by your when thinking about using the answer to GSI, right? Like 60 plus minus 5. But how do we determine those confidence intervals?
I think it's quality. So it's like if you ask different people to do it, you end up with, the reason why we say plus or minus 5, because we tried literally with some kind of experiments where we asked people to analyze GSI, and most of the time was plus or minus 5, and it was a good range. Actually, sometimes it was actually plus or minus 10. So, but you don't really remember, it's not measurement. So I think plus or minus 5 to give you some confidence, some ranges, but you can't really say even with Monte Carlo simulation because it's not a measurement GSI.
That's true. Especially how much minus do we put?
But to me, it's like people take classification, do GSI, and then they say, I want to be conservative, I'm going to put this value. Yeah, but you make it lower, lower, and lower. And again,
The probability for it to happen is low.
one time, it's kind of anecdote, but like I was many years ago when I was still a postdoc, they sent me to Davide to do some mapping and some looking at the stability of the pit. Shouldn't even mention that, but anyway, it's stable, so nothing happened. But I was looking at the pit, mapping is beautiful granite, very, very strong. There's some joints, but even if there's pressure, it's stable, no problem. And I was doing the model, it slide, and I said, and I remember the time was actually during lunchtime, and one of my favorite food is mashed potato. And I was like, my bowl mashed potato is more cohesion than my slide model. How is it possible that I put more cohesion based on mashed potato than actually the cohesion I use in my slide model? I'm so conservative. The plus is 2D, it will not fail because I designed it based on very, very conservative assumptions. So that's why I mean, you're going to be very, very basically conservative when you pick a data because it's a quality. It's not like you say, I have a ruler, let's call it 45 centimeters. Yes, different rulers from different manufacturers may give you plus or minus 1 millimeter, depending on the way they will be manufactured, but you know it's going to be 45 centimeters. So that's the value. Like it's in here is like, it's very difficult to tell. When plus is like, the problem with GSI then is like, at which scale you're going to measure it? And how do you get GSI from core logging? Which is when I designed to get it from core logging. So it's this number that fits into the Hook and Brown. And people sometimes think it as the number, I need to be very precise. It cannot be precise because no one knows what is the GSI of a rock mass. I mean, we can get very close to kind of a scatter, so we can be accurate, but we cannot be precise. Yeah.
Is there anything you think we should be careful about for adding classification that we call like qualitative or several categorization? There's a lot of space for qualification of case.
I think that the point there, like I was even thinking, okay, let's ditch the RQD, look at fracture frequency, which is a measurement. But when you look at core, how do you know which one is a mechanical fracture, which one is natural fracture? Then people's going to start assessing mechanical versus natural. And the typical approach in design is that if you're not sure, call it natural because it's conservative. At least that's what they say. If you put more fractures in a box, it should get more blocky, it should be more conservative. In open pit mining, yes. Tunneling, yes. If you're doing block caving, you're actually going to go the other way. more fractures in a box, in a blockade problem, the more I get convinced that fragmentation is going to be okay. I will not have any problems. So it's not conservative. So that's why, I mean, it's still based on someone deciding some kind of whether something is mechanical or natural, they kind of maybe push you in the wrong direction. But maybe you can look at, okay, how much kind of range can I get in plus or minus confidence if I get natural or mechanical? If I call them 10% of the time mechanical, 10% natural, what is the impact on my design? So to me, it's more like it becomes a sensitivity analysis. Not there's going to be one single curve for your failure envelope. It's going to be a range of potential kind of scenarios. Because I was working on another mine recently, and I did some simple RS2 problem. And I said, okay, let's start with this kind of, we have the UCS is between this range. You tell me the GSI is this range. I'm going to come up with 3 scenarios for UCS, 3 scenarios for GSI. I got a matrix. I'm going to see what is the risk if I use this, if I do models. At the same time, you're going to start developing your tunnels. This actually was a big chamber. So you have a top heading plus slashing on the side, then you go down. So as you do the first drill and blasting for 3 meters, you need to tell me what rock are you going to encounter? Is it good quality or bad quality? Because otherwise my model could be completely made up. So, and that's what we did is, okay, I have these scenarios, 9 different scenarios, it's from very, very good, from very bad. And then we see, actually, we are more in this range than this range. And then we selected support such that we can actually cover ourselves should you go really in a bad kind of scenario. That means that you can't simply do the design and finalize it until you start to see the rock.
No?
Yes. Thanks.
Okay. All right. Good. All right. Well, thanks. Awesome. So thank you very much. A little token of our appreciation. Sort of more. Yeah. Don't put this on your under the carriage of the airplane. Your prototype that you're flying. So thanks.
That's what I should make jokes about planes. That we go on the plane.
Right. Thanks very much. Thank you all very much.
Thanks.
And yeah, I'll whisk him off so he doesn't miss his airplane back to Vancouver. And thank you all for attending.
Yeah, just get my parachute.
Get the parachute ready to go. Yeah.